Welcome to lesson 5.3. This is fundamental theorem of line integrals. So, if you remember the fundamental theorem of calculus says that if you take the derivative, or no, not the derivative, sorry, the integral of a function f of x dx from a to b, then you will get the primitive of b minus the primitive of a. Or, if you guys don't know what primitive means, it's just the antiderivative. So, this would be if f prime of x is equal to f of x. That is the fundamental theorem for single variable integrals. This is the fundamental theorem for line integrals. So what does that mean? This means that if you take the integral of a function of a gradient field, has to be a gradient field, and equal to, so let f be a gradient field, and being a gradient field is the same thing as being equal to the, what is this, gradient of f, grad f, and let the endpoints of the curve C be P0 and P, with C in the direction of P. Then, if f is continuous on this path C, you get the integral of f dot dr is equal to the potential at P minus the potential at P naught. Pretty crazy, pretty nuts. It falls under quite like the same idea as this right here, but this is more useful for multivariable calculus, because you can go in multivariable calculus, you go in a bunch of different directions, and there is no fundamental theorem for just multivariable integrals, but there is one for line integrals. And why does it work? Well, because it ends up being, well, this is if you have a f is conservative. If the f is, I guess I don't think you guys know what conservative means, but if f is a gradient field, which means it's conservative, then you get a function, right? It'll give you a function. So because it'll give you a function, if I start in the set, let's say I start in the center. Let's say P0 is the center, right? And then if I go here to P, no matter what path I take on this surface, I'm still only going to move up this amount, right? No matter what path I take on the surface, I'm only doing that much work. I'm only doing work that will take me from the height of P0 to the height of P. I'm not doing any more work, right? With ones that are not conservative, I could be doing some more work. Yeah, like I could really I could draw a gradient field right now that's not conservative, but I'm not gonna do that right now. But with gradient fields that are not conservative, I'm gonna be doing work. I'm gonna be doing work differently depending on what path I take up there. But this is not conservative. This is not conservative, so you can make a function out of it. And if you make a function out of it, whatever path you take, whatever line integral you take from P0 to P, you will get the same result. And that's why you can do f of P minus f of P0 to get yourself the easier version of the line integral. Right, and you guys might say, well, isn't there going to be like a constant or a coefficient, or like a multiplier, like especially if you do electric field or if you do gravitation, you have to have like some type of mg factor into it. Well, that doesn't really, the line integral doesn't really do anything of that. That is just a kind of an add-on at the end, or at the beginning. So this is just to tell us what the vector field what the vector field does, what function the vector field gives, and if you do this, this is arguably an easier way to calculate your line integrals. All right, let's keep going. So here's some review. We're gonna find some of these, find the potential function for these vector fields. And oh gosh, we got a lot of problems today. Um, so we're gonna find a potential function for these vector fields. This is review. We already did this in 5.1, I think. So let's do it. So we're gonna say that this is f sub x is equal to 2y 3 halves. F sub y is equal to 3x times square root y. So if f sub x is this, then f is the integral with respect to dx. So 2xy 3 over 2 plus c, but the c is a function of y. And so if we take the derivative, then we will have 3x y to the 1 half y plus c prime of y. And c prime of y, you could see that it's 0. C prime of y is 0. So c of y is just a constant c. So therefore f is, in this case, 2xy to the 3 over 2 plus c. So that's the potential function for the first one. Let's do the potential function for the second one. It's a little bit harder, but we can do it because we're good at calculus. So let me just move everything up here. Okay, this is very, very messy. Very messy. All right, let's just shrink that. Do that. Shrink that. No, 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 no. Just do that. This thing won't work. Okay, this thing won't work for me. Whatever. So f is equal to 2xy to the 3 halves plus c. All right, what about e to the x sine y, e to the x cosine y? So e to the x sine y, what's the derivative of that? Or no, so f sub x, what's the integral of that? It is the exact same. It's the e to the x sine y. So e to the x cosine y. So the integral of this is e to the x sine y plus c of y, and then f sub y is e to the x cosine y plus c prime of y, but we have c prime of y is 0 again, so c of y is c. So f is e to the x cosine or sine y, e to the x sine y, and that is very, very simple. All right, now we're going to find the work done by these vector fields on the curve C. So we have a curve C, and we didn't specify what path it's going to take. We just start at 0 pi and end at pi over 2 pi over 2. So how do we know that? How do we know what the work done is? Just plug it in. F of pi over 2 minus f of 0 pi is equal to pi over 2 pi over 2. So we have pi over 2 times pi over 2 to the 3 halves. So it's 2 times pi over 2 squared minus 0 pi is 0, so 0. So that's the answer for the first one. And then for the second one, we have f of pi over 2 minus f of 0 pi. This is very messy right now, so I'm just going to go ahead and shrink this. There you go. F of pi over 2 minus, that worked for once. That was very, very nice. Pi over 2 is e to the pi over 2. Sine of pi over 2 is 1, so e to the pi over 2 minus e to the 0. Well, sine of 0 is 0, so 0. E to the 0 is 1, so it's e to the pi over 2. This is 2 pi squared. All right, that is how you find a potential function for the vector field. And now I'm going to introduce you to a little bit more vocabulary. If f is a potential function, f is also conservative. What's conservative? Conservative means that you will um, conserve energy. Conservative means that, well, one, it means that whatever path you take, you will always do the same amount of work. And it also means that wherever you are and whatever path you take back there, whatever path you take back to wherever you are, will be, you will have the same potential. You will have the same like number assigned to you. Like losing weight is definitely not conservative. But let's say losing weight, let's say it is conservative for a second. So if you go to Alaska or something, maybe if you're in Alaska, this won't might not work for you. But if you go to Alaska, you might lose 10 pounds. But if you go back to where you are at right now, you'll gain back your 10 pounds. That is what potential is. So if f is a potential function or a gradient field, if f is a gradient field, I'm sorry, gradient field. If f is a gradient field, then there is a value assigned to wherever you are at, right? If your friend is here, he might be 85 pounds. If your friend is in Alaska, the gravitation might be a little bit weaker there, so your friend might be 78 pounds. And then if your friend goes back to wherever you are right now, 85 pounds again. That is conservativeness, right? And gravitation is conservative. So if you go up a height, if you go up to a high height, 20,000 feet, for example, you will have this much energy on you. And then if you go back to the height, you will have this much potential energy on you. And it's the same for everyone. Well, not really, but it's the same for everyone with the same weight as you. So if they go to 20,000 feet and you go to 20,000 feet and you guys have the same weight, you guys have the same amount of gravitational energy. That's what conservative means, right? And conservative means that if you integrate to that point, and then you integrate a path back to that point, you will get 0. Now, if you go, this works for any. This next thing works for any integral. If you go, it doesn't have to be a gradient field. So if you go to from p0 to p, and you go on that same path, back, then you will always get 0 because it's doing the work and then it's doing the work on the opposite direction. So you always get 0. But for conservative fields, that's not the case. For conservative field, that is the case, but it's a lot more than that. If you go, for example, on this path, C1, and then you go on this path back, C3, you will get 0. Because that's what it means to be conservative. You are assigned a value everywhere you are at. And that value at that value, if you add to it by going to p and then come back at that value, you'll have the same value. So if you have the same value, there's no change, and you've done 0 work. Anyways, f is also path independent. Basically, what I just described, you can take any path to p, and then you will get the same work. Only works if f is a gradient field. So all of these is gradient field stuff. This is not a gradient field thing. This is something that works with everything. Um, However, if you go for a gradient field, you can go to p and then you can come back to p0 using any way you want, and you will still get 0. All right, find the work done by the vector field. Let's find the work done by the vector field. So, do we have any more questions? Oh god, oh god, oh god. I don't think I'll be able to do all of them. I don't think I'll be able to do all of them. All right. So this is f is yz, xz, and xy minus 2z. So this will be a little bit more hard, or a little bit harder. So f sub x is yz, f sub y is xz, and f sub z is xy minus 2z. So by inspection, I already know what this is going to be, but I'm not gonna try to surprise you guys. It's xyz minus z squared, but let's do it the way that I will want to do it. So f sub x means if you take the integral with respect to x, you will get x, y, z plus c. Is it c of x? No, it's not c of x. Is it c of y? Yeah, but it's also c of z as well, right? So this is actually plus c of y z. Why? Because if you take f sub y and f sub z, or if you take f and you take the derivative with respect to y or z, yeah. So if you take f and it has y and z stuff in it, and you take derivative with respect to x, and you'll get 0. That's why we have to have c of both y and z. Because if you take f sub x on this, you will get 0. So f sub y is what? Is xz plus c of c prime of y z, and c prime of y z is what? Or c prime of y z is 0. So what's c of y z? C of y z is a constant, but remember, it's not just a constant, because if we differentiated it with respect to y, then we could still have the z option left. So c of yz happens just to be c of 0z, or I usually just say c of z, and I'll probably write like c prime, but c of z works as well. So uh, so f sub y is equal to, or no, f is equal to xyz plus c of z. So f sub z is xy plus c prime of z, and now we notice that xy plus c prime of z and xy minus 2z, so c prime of z minus is equal to minus 2z. So c of z is z squared, or minus z squared. So f is xyz minus z squared. There you go. C is the curve from 1, 0, minus 2 to 4, 6, minus 3. So f of 4, 6, minus 3 minus f of 1, 0, minus 2 is equal to 4 times 6 times minus 3 minus 3 squared minus 1 times 0 times minus 2, which is 0, minus 2 squared. Which is equal to 4 times 6, that's minus 72, minus 9, and then minus a negative is plus, so it's plus 4. So that is minus 77. That's your answer. It's doing a negative 77 work. That means basically not working. It's giving energy. Well, work is a weird concept, but it's not working. It's not in the direction. It's opposite the direction. It's working against. It's working against is working against 77 is what I am going to say. All right, next one. Oh God. All right, we have a nasty ass function, and we have f. All right, so f is this. Well, first we can check for conservativity, but I'm not going to check for conservativity because that'll take too long. So f sub x is equal to 1 plus x y squared z squared. F sub y is 1 plus x squared y z squared, and f sub z. Did I make this question? Am I that sadistic? It's not going to turn out that bad, but so f would be x plus x squared y squared z squared over 2 plus c of y z. That means f sub y is 2x, or no, not 2. x squared yz squared plus c prime of yz, and c prime of yz is 1. So c prime of yz is 1. So c of yz is y plus c of z. Y because the antiderivative of 1 is y, but there is a c as well, and a c of z, because if you take c with the derivative of c with respect to y, I guess to make it clearer, I should do this. So c sub y of yz is 1, so c is y plus c of z, because if you take the derivative of c of z with respect to y, you will get 0. So it's y plus c of z. Okay, so then now you'll have f sub y is x squared yz squared plus y plus c of z. So f is, or no, sorry. F is x plus y plus x squared y squared z squared over 2 plus c of z. So f sub z is x, or no, not, yeah, x squared y squared z plus c prime of z. And c prime of z is 1, so I'm not going to write that work again. F is x plus y plus z plus x squared y squared z squared over 2 plus c. Holy crap, that was a mouthful. All right, that's a lot. That's a big number. C is the curve defined from 0 to t to pi, and our curve is this, right? So what now? Can we use the theorem in this case? The answer is we did all that work to not be able to use the theorem. Why? Because 3 secant t right here is 3 over cosine of t, which is discontinuous at t equals pi over 2. So we cannot find the line integral in this case. We'd have to do something else. I don't want to do something else right now, and you haven't learned enough to do something else, so I'm just going to write cannot use fundamental theorem. Cannot use fundamental theorem. I guess that's why I made the function, the gradient field, so hard, because I wasn't going to do that much work anyways. So cannot use fundamental theorem of line integral. Alright, this is a little bit simpler. This is only 2 dimensions, but let's see how simple it really is, I guess. So f sub x is negative y over x squared plus y squared. Wait, that's really hard. And then f sub y is x over x squared plus y squared. No, I don't think that's that hard, actually. I think that's doable. I think it's just arctan. Alright, so if that is that, then if you know the identity is, or the integral of 1 over a squared plus x squared is equal to 1 over a arctan x over a, right? So that is your, if you know that identity, I think it should be easy. So then you y. And c prime of y is what? C prime of y is nothing, so it just ends up being c. So f is negative arctan of x over y plus c. That was crazy. Alright. So r is this, 4 cosine t, 4 sine t. So this is continuous. It is actually continuous this time. But we have, the c is a curve defined from 0 to 2 pi. So what does that mean? That means that we have to figure out where the curve starts and where the curve ends. How do we figure out where the curve starts or ends? By using this position function right here, r of t. So r of 0 is what? R of 0 is 4 cosine 0, 4, and 4 sine 0, 0. What is r of 2 pi? R of 2 pi is what? R of 2 pi is 4 cosine 2 pi is 4, and 4 cosine 2 is 4 sine 2 pi is 0. It's the exact same point. Because it's the exact same point, and we've proven that it's conservative right here. So it's conservative because we can find a function for it. We could also have done the curl thing. Actually, that's the next video. Yeah, but it's conservative because we've proven that there's a function right here. We could have done m sub y minus n sub x or some shit like that. We could have done that as well. But we've proven that it's conservative. So what does that mean? That means the integral of f dot dr along the curve c is 0. Doesn't do any work because it's conservative, because it's a gradient field, path independent, whatever. But it stays at once. It just makes a whole circle back to the same place. So because we can find a gradient field for it, 0. All right, that's gonna be it for today's episode. If you enjoy, hit the like button, share it to your friends, share it to people who are struggling in physics, and I will see you in the next video.